Ladies and gentlemen, please welcome Robin Bordoli, CEO, Crowdflower.
Good afternoon, everyone. For the next 20 minutes, I want to take you all with me on a brief history of AI. Like the great Stephen Hawking, I'm going to attempt to take a vast and complex topic and make it more accessible to a wider audience. And I'm going to do that by only using one equation. So let's start by going back in time to 1956, 61 years ago. 61 years ago, four trailblazers, John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, convened at Dartmouth College for an 8-week summer workshop. And it was there that John McCarthy first coined the phrase artificial intelligence. It was an ambitious working group. What were their goals? In their own words, an attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. That's my emphasis. So, like most trailblazers, they probably didn't realize how hard it was, the path that they were starting on. So how did they do? Well, over the next 4 decades, there were a number of important advances that were made within the research world, but the real-world applications were few and far between. And in many regards, it was a winter wasteland for commercial applications. But then let's come forward in time to 1997, when we had the first astonishing milestone and breakthrough in AI. Garry Kasparov was beaten 3.5 games to 2.5 games by IBM's Deep Blue. This was the first computer program that defeated a world chess champion in a match under tournament conditions. Now let's fast forward another 19 years to just 1 year ago, 2016. This time, the game was the Asian board game Go. And this time, Lee Sedol, who was an 18-time world champion, was defeated by AlphaGo, which was a computer program run by Google's DeepMind. And this was the first time a world champion at Go was defeated by a computer program in a match under tournament conditions. Now, for those of you who aren't familiar with Go, you may think it's another board game. So it's just like chess, right? It's just a little bit different. No, it's fundamentally different in 2 ways. The first, rather than 8x8 board, it's 19x19, so the game playing space significantly larger. But the second, perhaps more important point, is the way you win in Go is you actually encircle your opponent's pieces, whereas in chess, you just take a single piece. Those 2 things make this game dramatically more complex than chess, which is why it took 19 years. Let me put some context around that. The number of atoms in the known universe is 10 to the power of 80. The number of possible Go game positions is 10 to the power of 170. Now, our minds struggle to understand those numbers, so let me give another example of this. Imagine if each of the known atoms in our universe got expanded to become an entire universe itself. And every single one of those atoms happened. So each atom expanded to an entire universe, and then you've got the same number of known atoms in each of those new expanded universes. The number of known atoms in that new expanded universes would still be less than the number of Go game positions. So this was an astonishing breakthrough. So now let's fast forward to this year. What amazing, astonishing AI breakthroughs have we had? Well, maybe not so much. Here's an example of an AI failure. This was a few months ago in an office complex in Washington, D.C. They had attempted to replace a security guard with a robot that would go around patrolling, making sure nothing untoward was happening within that office complex. But unfortunately, it went into the water fountain and unintentionally killed itself. So a dramatic failure. So how do we reconcile these two extremes of achievement on the spectrum of AI? We have a computer program that is better than every single human on the planet at a complex game. And then we have these failures where they unintentionally kill themselves, and what is a seemingly straightforward task, they fail at. How do we reconcile these two? Where is AI truly in the real world? And the answer to this lies in the real world. Our world is messy and complex and a little confusing. And let me illustrate that with some artwork from the incredibly talented Karen Zach, who's an art director at Whedon and Kennedy. To illustrate this, if you look on the left-hand side and you look quickly, can you discern what's a muffin and what's a chihuahua? You look on the right-hand side and you look quickly, can you discern what is a puppy and what's a bagel? So this illustrates how messy and complex and nuanced the real world is. And this is why it's hard for AI to fully operate in the real world. So to do that, for AI to operate in our messy human world, we've actually got to explode 5 common myths about AI to make progress in this. So myth number 1, AI is a magical algorithm. Now this myth is perpetuated by Hollywood. If you look at Her and Ex Machina, you see examples of computer programs or robots effortlessly mastering their environment. That's a myth. The truth, and here is the one and only equation I'm going to use today, is a little different. So this is the equation. This is the one equation to remember from today. AI equals TD plus ML plus HITL. So let me define these terms. TD is training data. ML is machine learning, the algorithmic component. And HITL is human in the loop. So let me quickly define each of these. Training data is taking data from the real, messy human world, text, images, video, and audio, and adding labels to that so it's structured in such a way that the algorithm can learn and understand. That's the concept of training data, adding an output to an input. Now, if you've been around children when they're 9 to 12 months old, you already understand this concept of training data. It's at this point that they start to point at things. They go chair, ball, cat, dog. They are labeling entities and training their brain on that entity so the next time they see it, they can recognize it. It's no different for computers. For example, when a computer sees an image, the first thing they see is pixels and colors. They don't understand entities like you and I, and they have to be trained that a particular configuration of colors and pixels represents a specific product, or in this particular case, a specific beer brand. Likewise, in the autonomous vehicle space, they don't understand these colors and pixels until they are taught. So they have to understand every single pixel to understand what is a drivable surface, what is a pedestrian, what is a road sign above a road, what is the sidewalk. These are examples of training data. So from that training data, you can now create a model. That training data is giving an input and an output, and then from those inputs and outputs, the model is trying to understand the why. For a given input, what should the output be? So in the autonomous vehicles case, imagine now the input is a raw image, a raw unstructured image. And this particular model is trying to identify pedestrians. So it would bring in the image, it would apply the algorithm, and it would give you an output. It would see, over here is a pedestrian. Because it would have learned these particular configurations of colors and pixels is this entity called a pedestrian. Now, machines will do something else that humans really struggle with. If I ask someone to give a prediction about something, and then I ask them how confident they are about that prediction, they'll struggle to tease those two concepts apart. By nature of giving a prediction, we feel we have to be confident. Machines have no such qualms. They can look at the particular example and say, look at this particular example of a pedestrian. Let me look back at the millions of examples in the training data I've learned from, and how similar or different is this particular configuration of pixels and colors, and therefore give a prediction. So it could say, I'm predicting this over here as a pedestrian, but I'm only 67% confident, which to our human ear feels odd, doesn't it? It's like either there is a pedestrian or it isn't. But that's one of the differences with machines. Which brings you to the third part of the equation, human in the loop. Human in the loop takes advantage of that confidence level and says, if it's above a threshold that's acceptable to you and your business and organization, then accept it. Take that output from the model. If it's not, if it falls below, then you actually need humans to come in and override and take over that particular example. So I don't know about you, but if I had a model that was giving an output of only 67% confident about whether that's a pedestrian or not, I would want a human to take over that particular judgment or output. So when humans then take over, that then becomes new labeled data that goes back into the model and continuously improves it. So in this way, you get a blended output, part human, part machine, and you're continuously training and teaching the model where it fails. So the truth is that AI is not about a magical algorithm. It's about training data, machine learning, and human in the loop together. All right, myth number 2. AI is only for the technology elite. If you see all the mainstream media coverage, they're talking about Apple and Microsoft and IBM and Amazon and Facebook, Salesforce, Tesla, Google, and Uber. They're positioning this as technology titans on the field of play, bashing each other's brains out. That's not the case. AI is for every business. It's for every one of you and everyone here at Dreamforce. So why do I make that claim? Well, 61 years after those 4 trailblazers met at Dartmouth, we're finally at a state where the base conditions are in place for AI to work for every business. Those 5 conditions are compute power, storage capacity, the data that is now being generated through cloud and mobile usage, data scientists, the ability to have people who understand data and can derive business value from that data, and then finally, machine learning in the cloud, having algorithms and models in the cloud from companies like Amazon and Microsoft and Google and Salesforce and IBM. So they're now in the cloud and available. So what that means is there are 35,000 companies today in the US that have at least $50 million in revenue. And for those companies, they can spend less than 0.2% of their revenue to start to apply AI to their business, because cloud economics now mean it's a 6-figure investment to start. You go back 2 years ago, it would have been a 7- or 8-figure investment for a company to start to apply AI to their business. So myth number 3, AI is only for billion-dollar new problems. You know, the media coverage is around autonomous vehicles. It's a very emotional, interesting topic. You've probably all seen them this morning around the streets of San Francisco. Or it's about drone delivery, taking drones from the military world into the commercial world. But the truth is that AI is also for million-dollar existing problems, things that might seem mundane or a little boring, but have tremendous business impact. So an example of that is categorizing support tickets. So no doubt a number of you in the audience Salesforce Service Cloud customers, and you're dealing with a torrent of online feedback. Your customers increasingly are giving you feedback through email, through chat, through social channels. And that feedback typically will be in the form of an unstructured, text-based conversation. So the question is, if you were to apply AI to that problem, how would you go about doing it? So you would start with the training data. So you would start with tens of thousands of support tickets or text-based conversations. And you might start with defining, first I want to define what the topic is, and I want to define the level of importance. If I can apply AI to that problem rather than humans, I can actually respond faster and more effectively and serve my customers better. So the training data will have the input being that text-based conversation back and forth between your company and the customer, and then two labels, which is the topic and the level of importance of that particular issue. So from that, you create a model. From that, you would start to put your new support tickets through that model. And it would apply those labels. It would apply the topic and the level of importance. And importantly, it would also give you the confidence threshold for each of those. And you could determine, based on that confidence threshold, which of those do you allow the model to take over, and which of those still require human intelligence to be applied as well. So, myth number 4, algorithms are more important than data. Again, the media coverage talks about this magical, mystical algorithms. We're going to flip a switch, and AI is going to magically work. Well, within the industry, we've known for a decade or so that actually data is as important, if not more important, than the algorithms. This paper, written back in 2009, so Alon Halevi, Peter Norvig, and Fernando Pereira. Peter Norvig is talking later on today on an expert AI panel. And they published a paper called The Unreasonable Effectiveness of Data. To summarize it in layman's terms, they said, if you had a choice between making better algorithms or getting more data, get more data. Another example of this, seem to have lost the slides. So another example of this is a company called Kaggle. So Kaggle is a competition platform for data scientists who want to compete at building machine learning models. And companies and organizations like Department of Homeland Security, GE, Zillow, publish these competitions and allow data scientists and machine learning engineers to compete to see who can build the best algorithm, the best model. We did one of these. Our company did one of these, and it was a prize of $20,000. So, real money. So what happened? So over the 8-week competition, there were 1,300 teams that competed to win this $20,000 prize. And a team could be one person, or it could be, as many as 10. People self-assembled and decided what the composition was of their teams. And then the right-hand side, if you look at the model accuracy. So in the first week, it went from about, the best model went from 30% to about 65%. You see, at that time, there were about 200 teams that were competing. Over the next 7 weeks, 1,100 new teams came on and continued to compete. So you can see it was intensely competitive. But the model only crept up a little bit, went from 65% over the next 7 weeks, and a new 1,100 teams, it only crept up to 70%. You could see it effectively flatlined. So this is what happened when everyone had the same training data set, and you just improve the algorithm, you rapidly get to diminishing returns. Another cut at this is to look longitudinally. If you look at 6 of the major breakthroughs in AI over the last couple of decades, and you look at when was the first algorithm proposed for this problem, and then when was the data set available, on average, the breakthrough happened 18 years after the algorithm was available, but only 3 years after the data set was available. So the data set was the bottleneck in this case. So the truth is that training data is as important as the algorithms. So the last myth number 5, that AI is about machines replacing humans. This is probably the most pernicious because it's the one that drives our collective fear and sense of anxiety and identity. So when these major milestones happened, they're emotionally heavy events. They get cast as machine defeats man. Now, that's an incorrect framing. The right way to think about this is not a single machine defeats a single human. The right way to think about this is a single machine plus thousands of humans that played the game of Go or game of chess and that machine learnt from, defeated a single human. So if you frame it that way, it feels like an unfair fight, and in some regards, not an unexpected outcome. So this is why we should think about the combination, not the replacement. And I'll give an illustration of why that is. Machines and humans are different. We have different relative strengths and weaknesses. Machines are have fantastic computational power. Humans, our strength is understanding context, understanding meaning, operating in this messy human world, in this ambiguous environment. So most all machines would pass that problem on the left, finding the eigenvectors. Most humans would fail at that. Most machines would fail at the problem on the right, finding the leopard print dress, because they don't understand the entity. They might just look for the leopard. They might just look for a dress. They might look for a print dress. They might look for a leopard print. So machines would struggle with that, understanding the context and the meaning. So this is why AI is about the combination. Humans create the training data and provide the human in the loop to gracefully handle the fail states when the machines fail. And the machine handles the vast amount of data and to be able to objectively understand the confidence around a particular output as well. So it's the combination of these. So the way to think about business processes is not machines replacing humans, but augmenting. So if you think about a business process over time, it may start as 100% human, categorizing support tickets, having conversations with customers. Those will be 100% human, and you might start to automate some percentage of it. But over time, as that human in the loop becomes new training data and improves the model, the percentage that the machine can handle will increase. But as a result, the volume of the work you can put through the business process will also increase. So we will continue to get this combination. Now, we don't just have to imagine that. We can actually learn from a real-world example. So the US Postal Service, 52 years ago, started applying optical character recognition to identifying and sorting envelopes based on the address. Today, 99% of that is automated, and they handle 500 million mail pieces a day. And so 5 million are still handled by humans in the loop, even 52 years later, that 1%. So the truth is, AI is about machines augmenting humans. So I've just spent time looking back over the last 61 years, back to 1956, when those 4 trailblazers started in Dartmouth. Let's spend a couple of minutes looking forward to the near future, the next 3 years. So it's clear the number one challenge for AI is how to operate in this messy human world. So a couple more wonderful examples from Karen Zach. So on the left-hand side, understanding between labradoodles and fried chicken. On the right-hand side, understanding between pugs and croissants. This is the messy human world that AI will have to operate in. So the 5 truths that I'd encourage you to take away back to your companies, your organizations. For AI to triumph in the messy world, remember these 5 truths. AI is TD plus ML plus HITL. That's the one equation. AI is for every business, not just the technology titans, because of the economics of the cloud. AI is for million-dollar existing problems, like categorizing support tickets, not just the glamorous billion-dollar problems of autonomous vehicles or drone delivery. 4, training data is as important as the algorithms because it's the training data that teaches the algorithm about this messy human world. And then finally, don't be worried. AI is about machines augmenting humans. We have different relative strengths and weaknesses. So if we can stay true to these 5 truths, then the vision that those 4 trailblazers had 61 years ago has a chance of coming true. Thank you very much and enjoy the rest of Dreamforce.